Hi. Now, in previous videos, we have talked about Gauss's law, right? Now, in this video, we're going to talk about a different way to state, in fact, more than one different ways to state Gauss's law when there is a dielectric in the picture, right? So, let's start with the normal statement of Gauss's law, which is that integral over a closed surface E dot ds, right, is equal to Q inside upon epsilon naught, but this is the charge inside the Gaussian surface. Okay. Now let's take a scenario where there's a dielectric present. So how can we state it more conveniently, right? So let's say there is a parallel plate capacitor. So let us say this is one plate, this is another plate of a capacitor, and it is filled with a dielectric, right? So it is filled with a dielectric, right? And now let's say we connect this to say some battery, right? And because of that there is some charge. So there is charge, let's say plus Q naught and minus Q naught on the two surfaces, and in the dielectric there'll be some induced charge, and let's say that is minus QP and plus QP. Right? So now if I were to state Gauss's law normally, so this is the normal statement of Gauss's law, and I could take a Gaussian surface here. So let's say I take a Gaussian surface here, right, which passes through this and this and this and then comes out here, right? So it's a kind of rectangular surface, right? And it goes to so the top portion is in the conductor and the bottom portion is in the dielectric here, right? Now if I apply this law here, what will I say? So I'll say the same thing, and this would be, so here this would be integral E dot ds, right? That would be equal to Q inside. Now what is Q inside? Q inside upon epsilon. What is it? This is going to be Q naught plus QP. Remember, both the charges minus QP and this Q naught would be here, right? This would be this would reside on the inner boundary, right? So you'd have plus so on, right? And then you would have here these minus charges, right? So this would be equal to Q naught, right, minus QP, right, upon epsilon naught. Right? Now what is QP? This is the induced charge, and we have discussed that, if the dielectric constant is K, right, then we know that QP is what? QP is equal to Q naught, right, into 1 minus 1 upon K, right? This we have discussed, refer to a previous video, there we have, derived this, right? So just substitute this here. So what will I get? So I'll get E dot ds, right? This is equal to Q naught minus QP, which is Q naught into 1 minus 1 upon K, right? And if you open this up, what will you get? You'll get Q naught minus Q naught, right, plus Q naught upon K. And these two cancel out, and then we have this is equal to Q naught upon K, and therefore I can write this as integral K into, I'm sorry, here there is this whole thing, there is an divided by epsilon naught, right? So again, divided by epsilon naught here. And then I can write this as integral K, right? Integral K E ds, right? This is equal to Q naught upon epsilon naught. And what is my Q naught? Q naught is my free charge, right? This is a charge which is, so this is not, we're not talking about the charge induced, we're talking about the charge actually flowing. So this is the free charge, right? So I'm going to now write this as, so, and this is the alternative statement of Gauss's law, which is integral over a closed surface K into E dot ds, right? That is equal to Q free, right, upon epsilon naught, right? This is same as this, but this is in the presence of a dielectric, with a dielectric constant K, right? So we can use this form. So these two are equivalent. This one here, it tells he gives me the value of this integral in terms of Q free, right? In terms of Q free, which is something that we can easily measure, right? Okay, now there is Now this is one statement of, rather one alternative statement of Gauss's law. Now there is another way to state that. How would that be? So now let's say I multiply, so let's say let's look at, KE, right? So now my KE, right? What is KE? K into E would be equal to E naught, which is the electric field only due to the free charge, right? Why is that? Because we have defined K as electric field, total electric field is equal to E naught upon K. Therefore, this is there, right? Now what is the electric field, total electric field inside here? This E, right, is equal to E naught plus the electric field due to the polarization, right? This is total electric field, right? Now what is the now how do you find what is EP? Right? Now EP, just look at this capacitor, right? So here my E naught will be what? So E naught, right? E naught would be nothing but sigma naught upon epsilon naught, or sigma naught is nothing but Q naught upon A epsilon naught. Right? And what is my my EP going to be? So now look at this. So this plus QP is minus QP, right? Now I'll go back to what we had defined earlier, or we talked about polarization vector. Now I'll give it a mathematical definition, right? So let me now refer to the polarization vector, right? P, right? What is polarization vector? Polarization vector is nothing but it is the total dipole moment per unit volume, right? Now look at this here, right? What is going to be the total dipole moment, right? So let's say we have here minus QP and here plus QP charges, and the distance between them is D. This distance is D, right? So what is the so if you look at any charge here, there's a corresponding charge here, right? So there'll be a dipole moment which should be the Q, the charge into this distance, right? So the total dipole moment is going to be nothing but QP into D, right? This is minus QP, this is plus QP. So the dipole moment would be total dipole moment would be QP into D, right? But P is the dipole moment per unit volume. So if I take the magnitude, right, this is going to be what? This is going to be equal to QP, right, into D, right, divided by volume. What is the volume? Volume is going to be nothing but A into D, right? So my why A into D? Because A is the area and D is the distance, right? So this is cancelled. So now what is QP upon A? This is nothing but the surface charge density, right? So I'll write this as sigma P. Sigma P is the surface charge density. So this is an interesting result, that the polarization vector, right, its magnitude is equal to surface charge density, right? So this is the result that I'm going to now use here, right? So my electric field would be, E is going to be equal to, what is E naught? E naught is the electric field because of plus Q minus Q, that would be sigma naught upon epsilon naught plus EP. Now, what would this be? So this is going to be, in fact, let me do one thing. I'll skip this. I'll just retain this E naught, right? So E equals E naught, right, plus EP. What is EP? Now EP is going to be nothing but sigma. The magnitude is going to be sigma upon epsilon naught, right? So its magnitude of EP. I'll write this here, right? Magnitude of EP, right, is going to be sigma P upon epsilon naught, right? Now we know sigma P, its magnitude is equal to P, right? But what is the direction? The dipole moment goes from negative to positive, but the field is going to be upwards, right? So we can say that this field EP would be nothing but minus, right? Minus of P upon epsilon naught, right? Why is that? Think again, right? This vector P is in the downward direction. Remember, dipole moment, the direction of dipole moment vector is from the negative to positive. So my P vector would have this direction, right? But my electric field EP has got the opposite, this direction. This is the direction of EP, right? So, and its magnitude, right? Since EP magnitude is equal to sigma P upon epsilon naught, but sigma P is nothing but P, right? So this is another way of writing. This is another way of writing sigma P upon epsilon naught. But sigma P is same as same as P, right? So now so now with this I can say that my E0 vector is equal to E plus P upon, just taking it here, P upon epsilon naught, right? Now if you look at this equation, what is KE? KE is nothing but E naught, so I can write this equation as integral, right? E naught, right? E naught ds, right, is equal to Q free upon epsilon naught. Okay? Now look at this. What is this? E naught is equal to E vector plus P upon epsilon naught, right? So now I can write this as integral, right? And if I multiply this, it will be epsilon naught E naught, right, ds is equal to Q free, right? Q free, and what is epsilon naught E naught? If I multiply both sides by epsilon naught E naught, I'll get here epsilon naught E naught, right, is equal to epsilon naught E, right, plus P. Right? Now I'm going to give it a convenient name. I'm going to call this. So this is an electric field vector into epsilon naught, some constant, plus the polarization vector. I'll call this a displacement vector. Call it a displacement vector D. D, it's called displacement vector. Displacement vector. Okay, and with this definition, now look at this. What does this become? This becomes nothing but this is equal to this. So this is my displacement vector. So I can write this as integral D dot ds is equal to Q free. Okay. I'll just mark it separately so you can see it clearly. Right? So there are two alternative statements. So one statement is that, so this was the original statement. One statement is now in terms of the free charge. One is K EDS is equal to Q free upon epsilon naught, and second is integral D dot ds is equal to Q free, right? So these are some of the statements that you'll be using, some of them this will be using immediately, and some of these they have applications in higher physics. Thank you.